Good day, everyone. We're going to start lesson 2.5 today. The title is Implicit Differentiation. So our main objectives today is for two things: introduce to you the term explicit and implicit form for an equation. And the second is to introduce the process of what's called implicit differentiation. That's finding the derivative of an equation that is in what's called implicit form. Now, what I thought we should do first today is kind of review different uses of the chain rule for derivatives, what we just finished working on, and what we just finished introducing in the last series of lessons. So I've got a couple of functions here that are all, the first three are composite functions, meaning there's one function inside of another one, and we want the derivative of that composition. So I put a note here at the top. We want to think in our head, in our mind, that the way we used the chain rule was we replaced or thought of the inner expression in our composition as u, or just named it u, and then that allowed us to rewrite the function in more basic form. And then the chain rule said just to multiply those two functions' derivatives together. So for example, in the first one, if your thinking is let u be g of x, then the function, the expression g of x to the fourth could be thought of as u to the fourth. And so then my derivative with the chain rule would be first the derivative of u to the fourth, which is 4u to the third. And so there it is. But now I'm just going to call u g of x again. So it's 4g of x cubed. And then in the chain rule, we always multiply by the derivative of u. So u prime would be the same as g prime. So the thinking here is this is similar to the simpler form, 4u to the third times u prime. Okay, but u is the stand-in for g of x, so it's 4g of x cubed times g prime of x. Okay, the other two coming after that work the same. If you think of square root of g of x, if you're thinking of it as just the same thing as writing square root u, then our derivative requires the chain rule, and so f prime of x would be, remember that the derivative of square root x, or square root u, is 1 over 2 square root u. Then there's my derivative of the square root function, and then there's the derivative of u, g prime. So my f prime is 1 over 2 g of x, square root of g of x, times g prime of x. You could also then write this as g prime of x over 2 square root g of x, because you're just combining two things here. This is like over 1. The third one is like it's e to the g of x, but if you replace this with a single variable, it's like writing e to the u. And the derivative of e to the u is e to the u. It's its own derivative, but with the chain rule, we always multiply by the derivative of u. So my derivative is e to the g of x times g prime of x. So all three of these are examples of applying the chain rule. The fourth one really is the product rule. I've got the function g of x multiplying by the variable x, or just you can think of this as a function x, function y equals x. And so this derivative requires the product rule. As we say, 1 d2 plus 2 d1. Anytime I say the 2, we're talking about g of x. So 1 d2 is x g prime of x, and 2 d1 is g of x times 1. All of this will come in handy today as we start our lesson. Okay. The other warm-up activity today is to look at this, what looks like a calculus problem, because in our calculus class, we've been doing lots of talk about graphs of functions and tangent lines, and using derivatives to find the slopes of tangent lines. Well, this could be a calculus problem, but it doesn't have to be, because this particular curve is a circle, and we have drawn a tangent to the circle. And the question here is, without using derivatives or calculus, can we decide and determine what the slope of the blue tangent line is? So you have to know three important facts from your prior math classes. The first one is, what is the relationship between this tangent line to the circle and the radius of the circle? What you learned in your geometry class is that if I draw a tangent to a circle, mark the point of tangency, and then draw a radius to the center of the circle, the radius and the tangent line always are perpendicular. So there's a right angle right there between the tangent line and the radius. And that allows you to now think about slopes, because using the radius that connects the point 3, 4 to the point 0, 0, we can work out that the slope of this line, I'm going to put slope of the radius, is clearly, it's rising 4 and running 3. However, because the tangent is perpendicular to that, then you learned in your algebra class that if you have two perpendicular lines, the slopes are opposite and reciprocals. So for the slope of this tangent line, it should be the opposite and reciprocal of 4/3. It should be -3/4. Notice that the 3 and the 4 are in the ordered pair, and the 3 was the x-coordinate and the 4 was the y-coordinate. What I'm going to try and prove to you today as one of our first examples, introduction to implicit differentiation, is to prove to you that every point on this circle has a tangent line whose slope follows the same format. Okay, and so now in calculus we work with slopes and derivatives, but we only usually work with derivatives if we're working with what we call an explicit function, like y equals, and then we have an expression with x in it, something we could type into our calculator if we wanted to graph it. The equation of a circle that you're used to is one like this. The equation of this circle in standard form is x squared plus y squared equals, and 25 is known as the radius squared. The radius is 5, so the equation is x squared plus y squared equals 5. That is an equation that is not a function, is it? We can look at the graph of the circle and notice the vertical line test would fail. Any vertical line other than at the edges is going to cross through 2 points. Okay, so this is not a function. So we could not, this is not an equation we can type into our TI-84 and have it graph the circle. You actually have to outsmart this to graph the circle on your calculator. We have to come up with a separate function that draws like the upper half, because just the upper half of the circle would be a function. And we can come up with another function that would draw just the lower half. Okay? It's possible to do that with this one because I can easily subtract, I can get the y squared by itself by subtracting x squared. Okay, so this is just another way of writing this equation, that y squared is 25 minus x squared. But then to solve y equals, we actually remember that whenever I solve an equation by taking a square root, you actually have two answers. So in one side, we would have the positive square root of 25 minus x squared. That provides an equation that gives the y coordinate of, or all the points where the y coordinate is positive, and that is actually the function that draws the upper semicircle. Okay. But then we'd also have the negative square root function. And it is going to draw the points where the y coordinate is negative, so it's going to draw the lower half of the semicircle. I would encourage you to type both of these into your calculator. One of them could be y1 and one of them could be y2. And if you graph them both at the same time, you should see the two halves of the circle drawn in there. So together they make the entire circle, but this demonstrates what we call implicit form and explicit form. So I'm going to move to the next slide here and just introduce those two terms here. In the equation of the circle, in the standard form, it was written x squared plus y squared equals 25. Now that equation is not a function, but it actually implies two functions. it implies the explicit function y equals square root of 25 minus x squared. And it also implies this one, the negative square root, 25 minus x squared. These are equations that they are explicitly written y equals, and then you have a function of x here. Okay? And maybe you could call this one g of x, but it doesn't really matter what you call them. You have y equals, and then the expression on the other side is all in terms of x. In calculus, we've been working with our differentiation rules to study how to find the derivatives of expressions like these. Okay, so for example, we just learned the chain rule, and you would now be able to find the derivative of this expression here with the chain rule. Okay? But the goal today is to work with equations in implicit form and not have to know what the implied function is. And in some cases, you really have no way of knowing. Okay? But in this implicit form, it is just implied without being explicitly stated that y is a function of x. Or in the case of the circle, it's actually standing for multiple functions of x. Both this one and this one, both together, merge together to form this equation down here. Okay? And the name of that function really does not matter. So we could call it f of x or g of x or h of x or whatever you want to call it, but the notion is the implied part is that without explicitly saying it, we want to think of y as a function of x, meaning it would be not wrong to express the equation of the circle this way. And I'm just going to use the name g of x here. That if I want to think of y as a function of x, the equation of my circle could be written x squared plus that mystery function of x squared equals 25. And this is the way you want to think of equations today that are written in implicit form. An expression that contains y is really an expression containing the mystery function that is implied by the equation. So what I'm going to attempt to do now is work with the implicit form of this equation and show you that on the circle, as our first example, that the slope follows the format we got from the warm-up problem. Okay? And so I have the equation again, x squared plus y squared equals 25. What you want to think here, that y is always a function of x every time. Okay? So as I apply a derivative to this equation, you know, a derivative is like an operation. We can apply, if I have an equation with an equal sign, then the derivatives of the two sides would have to be equal too. Okay, so what we're going to be doing now is applying a derivative with respect to x to both sides. And because on this side I have addition, it means I can use the addition rule and find the derivative of x squared separately from the derivative of y squared. So I'm just going to write them all here. So now the plan of attack on each part is just a little bit different. Let's start with the right side because all I have here is a constant, and the derivative of 25 would have to be 0 because the derivative of any constant is 0. And then starting on the left side, the derivative of x squared requires just our basic power rule. The derivative of x squared is 2x. It's in the middle section where it gets a little bit interesting because remember, your thinking here is this is like y equals f of x. So the thinking is that even though I've got it written as y squared, you really could think of it as, and I'm going to just erase here, think of it like the warm-up problem where you have a function squared. Remember the warm-up problem? Now this looks like we're going to use the chain rule, because you could think of u equals f of x. This is the derivative of u squared, and the derivative is the power rule / chain rule. The derivative is 2u, in other words, 2 f of x to the first power times the derivative of the function f of x. Remember, the derivative of the inner function always ends the problem there. But it's way more cumbersome to write f of x than it is to write y. Okay, so if you were just keep in back of your mind that y is the name of the function, then I could much more easily have written this 2y times the derivative of y. And so anytime I have a term with y in it, you differentiate as usual, but always use the chain rule. So the derivative of y squared is 2y times y prime. Let's write it without parentheses, and then we're going to solve for y prime. So I've got 2x plus 2y times y prime equals 0. And now we want to solve for y prime. Okay? The term that has the derivative y prime is over in the middle, so I'm going to subtract from both sides of my equation the other term. And so now it says 2y times y prime equals minus 2x. So to solve for y prime, I have to divide by the other part. This is like the coefficient here. We're going to divide by 2y, and we're going to divide by 2y, and then simplify the answer because the 2's can divide and cancel. So my derivative, y prime, is the negative of x divided by y. Okay, so I want to scroll back to the picture of the circle a little bit ago and show you what this implies here. In our prior work, we noticed that the derivative, we found with the implicit differentiation, we came up with the derivative y prime equals the negative x over y. So what that means is not only does this is the derivative now, but it's the derivative or slope of every point on this circle, not just the upper half, not just the lower half, but all the points. So for example, if I wanted the slope that I found in the warm-up problem, it was the ordered pair was 3, 4. I can easily tell that would be right because the derivative was negative x over y. The x was 3 and the y was 4, so the slope would be negative of 3 over 4. But it would also work in the lower quadrant. So if I were, say, at the point 3, negative 4, the slope now down here, the derivative would be the negative of 3 divided by the negative of negative 4. Sorry, let me correct that. It's negative x over y, so it's negative 3, the opposite of 3, divided by the y coordinate negative 4. This time the negatives cancel, so we're at positive 3/4, and you can see that's what the slope of this line is, positive 3/4. So the nice thing here is this derivative involves both y and x. So in order to find the slope of a point, you would have to know the complete ordered pair, the x and the y. But if I do that, I can find the slope of any point on this curve. So we're going to move on to another example of where I would use an implicit equation and implicit differentiation to find a derivative and a slope.